Why do molecules take on the shape that they do? And how does this influence their reactivity? I'm Tyler Farah, and in this lesson on Vespr theory, these are two of the questions that we're going to tackle using no less a medically relevant example than that of penicillin. Specifically, we're going to compare and contrast two very common geometries, trigonal planar and trigonal pyramidal, and we're going to see why penicillin might prefer one of these geometries over the other and how that's going to influence penicillin's reactivity and overall stability. This is a very complex but very interesting question stem. So take a minute or so now and familiarize yourself with the question and the background that supports that question. This question stem starts by building up the structure of penicillin, focusing on its beta-lactam central functional group. Now, this might be a new functional group to you. However, you probably recognize the carbonyl group, and you might remember that when nitrogen is bound to a carbonyl group, that makes an amide functional group overall. So what a lactam is a ring-shaped amide, and you can remember this because the word lactam ends in am, just like the word amide starts with that prefix. They go on to describe that the functionality of penicillin really requires breaking that nitrogen carbonyl bond that is the key feature of this amide functional group. And they say something quite interesting. The question stem states that this functional group is normally very strong. But since penicillin's activity requires us to break that bond, there are a couple of features of the geometry that actually weaken the nitrogen carbonyl bond. So in this lesson, we're going to focus first on Vespr theory and why that explains how the nitrogen carbonyl bond is normally so strong. And then we're going to look at how penicillin deviates from normal Vespr theory and why that weakens the nitrogen carbonyl bond. To start with, let's acquaint ourselves with the actual geometry of a normal amide functional group. You might notice that on the far left, we have nitrogen forming three single bonds. And I want to start there. What geometry does nitrogen usually make in most instances where you see nitrogen bound to three constituents with single bonds? So nitrogen's usual single bond geometry is trigonal pyramidal. The reason why is that the three bonds that nitrogen makes are sticking off to the bottom, and the fact that those three bonds point downward makes space for nitrogen's lone pair, which has to take up space of its own. The overall resulting geometry sort of forms a three-sided pyramid, and again, this allows nitrogen to keep its lone pair separate from the rest of its bonding electron pairs. Coming back to our amide functional group, we're going to see that the nitrogen in an amide behaves a little differently from a normal nitrogen that's making single bonds. And to help explain that difference, I want to focus first and foremost on the atom that he's bound to. Let's look at this carbonyl carbon, which is exhibiting the textbook trigonal planar geometry. And let's start there. What is the dead giveaway? The obvious clue that carbon, in this case, is making a planar geometry. The clue that our carbonyl carbon is trigonal planar is the double bond. Whenever you see carbon making a double bond, that carbon is going to be a trigonal planar geometry. Now, given that, and looking over at the resonance structure that's available for the amide functional group, we can start to see why nitrogen is going to behave a little differently than normal. What would be the bond geometry around nitrogen in this amide functional group? In the resonance structure on the right, we see that nitrogen is definitely also going to be trigonal planar. Trigonal because nitrogen is bound to three different atoms, and planar because that double bond requires planarity. The next thing I want to look at with you is, one, to visualize what this looks like in three dimensions, and also to help explain why a double bond would require planarity. So focus your attention next on the molecule on the far right, which is a three-dimensional version of that amide functional group. We've now seen that the carbon-oxygen bond is a double bond in one resonance structure, and the nitrogen-carbon bond is a double bond in another resonance structure. The nature of resonance is such that actually both the nitrogen-carbon and the carbon-oxygen bonds have some double bond character, rather than one or the other being a double bond. So the question I want you to answer about this is, what goes into a double bond? What does the structure of electrons between two atoms look like when they share a double bond? A double bond consists of one sigma bond and one pi bond. The sigma bond is the connection directly between nitrogen and carbon or between carbon and oxygen. But to make those pi bonds, we need an extra set of electrons above and below each of these atoms. So you see a pi bond here and a pi bond up here as well. These pi bonds require extra unhybridized electrons that again exist above and below each of the atoms in the bond. And the important point is, in order to free up those electrons to make this pi structure, we need to have a planar geometry. Furthermore, this planar geometry is what actually allows the resonance, where electrons are shared equally between nitrogen and between carbon and oxygen. You know that resonance strengthens bonds. And so one of the reasons why the nitrogen-carbon bond in an amide is usually very strong is because it is resonance stabilized by this double bond structure. Another factor that normally strengthens this bond is the geometry around these bonds. We're asked here why the bond angles in a normal amide are distorted from ideal, but what we're going to see is that the distortions actually help the amide in this particular case. Let's start with the ideal bond angle though. And take a moment and answer this question. What is the normal bond angle in a trigonal planar geometry? The normal bond angle in trigonal planar geometry is 120. And the reason why is actually kind of elegant. There are 360 degrees in a circle. And in trigonal planar geometry, the atom at the center is trying to arrange its electrons so that they're as far apart in space as is physically possible. Well, if you take a circle, 360 degrees, and divide it into thirds, you get 120. So that's a neat explanation for why the ideal is 120. It basically spaces the electrons apart as much as possible. Let's take that idea of spacing electrons apart as much as possible and apply it to the normal amide, which you can see the bond angles are not exactly 120. For example, if you focus in on these bond angles around the carbonyl carbon, you can see that those bond angles in green are a little bit bigger than ideal. But my question for you is, why does this make perfect sense? Why would we expect those bond angles to be slightly larger than the bond angle highlighted in purple? The reason why those bond angles highlighted in green are slightly larger than ideal is all about the double bond. That double bond has twice as many electrons as a single bond has, and so those electrons need to take up a little bit more space. The point is, for that carbonyl carbon, these quote-unquote deviations from normal are actually a positive thing. They mean that that carbonyl carbon is making space for its extra electrons. Let's apply that same logic to nitrogen. You might notice that around nitrogen, again highlighted in green, there are a couple of bonds that are greater than ideal. But why would these bonds be perfectly happy being slightly greater than the ideal bond angle? In this case, the deviations from ideal are all about those resonance electrons that nitrogen is sharing with the carbonyl carbon. This amide functional group is extremely important in biochemistry. For example, the amide functional group is actually what holds together amino acids to make proteins. So you're going to see this drawn a lot in your practice before the MCAT and probably on test day as well. And it's worth remembering that nitrogen has those electrons that are resonating with the carbonyl carbon, even though the MCAT is almost never going to give you the hint of drawing that resonance structure. The point is, even though the amide functional group deviates somewhat from the ideal bond angles, it does so for very good reason and is actually more stable for it, even despite these slight deviations from normal. Now, let's get to the fun stuff. Penicillin is very much not a normal amide. We saw in the question stem that penicillin features this beta-lactam central functional group, which is like an amide that's been distorted into a four-membered ring. We're going to see that ultimately penicillin uses this distortion to facilitate its actual activity, which, remember, requires the breaking of that nitrogen carbonyl bond. Let's start now to see why these deviations from normal help break down that nitrogen carbonyl bond. What about this beta-lactam structure would make it very, very much destabilized compared to the normal amide that we just saw? Looking at this molecule, a four-membered ring is going to assume a square shape. And that means that we can use basic geometry to infer that the bond highlighted in yellow in the inside of this square would be around 90 degrees. It may not be exactly 90 degrees, but the point is it's very, very far from the ideal 120. A little bit of arithmetic gets us bond angles of around 135 degrees there in red outside the square, and the same would be true for that carbonyl carbon. In this case, we're seeing huge deviations, and these don't benefit nitrogen or carbon. They don't stabilize those atoms. Rather, these are the necessary bond angles to get into that square geometry in the first place. We call this great deviation due to ring structure ring strain. And the big problem with that is that it brings the electrons of this bond and the electrons of this bond much closer together than they'd like to be. Electrons, being like charges, are going to repel. Repelling means increased energy, and guess what? Energy is exactly what's required to break bonds. And that all leads us to our final prompt, which is going to help us explain the reactivity of penicillin. What we have here on the screen now is the functional group at the center of penicillin, now rendered in 3 dimensions using some of the Vespr geometry we've discussed in this lesson. The key idea here is that not only do we have a 4-membered beta-lactam ring, which you see on the right side of this diagram, we've also got a 5-membered ring fused onto that 4-membered ring. Now, you might recall from your previous study the shape of a 5-membered ring. If not, you kind of get a hint from the geometry drawn on screen. But take a second and think about this, or maybe look it up if you have to. What shapes do 5-membered rings consisting of all single bonds usually take on? The shape of 5-membered rings is usually described as the envelope shape. And you can sort of see why. This kind of looks like an envelope that's been opened, and that's where we get the name envelope geometry from. Time for the grand finale. Taking a look at nitrogen, let's see how being fused to that 5-membered ring affects the geometry. Basically, nitrogen can no longer be flat because of its location relative to the 5-membered ring. In fact, looking at the geometry around nitrogen, you might recognize this shape. What geometry is nitrogen now taking on? The substituents bound to nitrogen now take on the textbook trigonal pyramidal geometry. The last and most important question is why this influences the reactivity of penicillin. What about this new geometry helps break that nitrogen carbonyl carbon bond? The reason why this bond is weakened by the trigonal pyramidal geometry is that nitrogen's electrons are now held clearly above the pyramid. Remember that for double bonds and for resonance, we needed some electrons both above and below a planar structure so that those electrons could be shared between nitrogen and carbon as a second pi bond. Without the planar geometry, we can no longer have that double bond character, we can no longer have that resonance stabilization, and without resonance, that's going to help weaken and ultimately break that nitrogen carbonyl bond. The point here is, in short, distorted bond angles plus loss of resonance equal weakened bond overall. In this lesson, you saw that Vespr theory is about a lot more than just molecular geometry. The very reactivity and behavior of molecules themselves is determined by their overall shape. Now, there are a lot more geometries than just trigonal planar and trigonal pyramidal for you to learn before the MCAT. But I hope now, as you go out and learn those other geometries, you have a little bit more context about why these are important even to doctors.